So now let's look at a couple of particular cases that are maybe a bit more interesting than just weird powers and weird other stuff. And this is sort of more from the calculus point of view, because these ODEs with regular singular points have the nice property that, well, of course you can sort of solve them analytically away from their singularities, but you can actually solve them by expanding around the singularities. So given an ODE with regular singular points, we can look for the answer, look for the solution. Not only away from the singularities, but around the singularities. By means of the Frobenius method. And the point is, or the idea is to have as an ansatz not a power series, but like a power series multiplied by some non-natural power. So one example we look at now is the equation second derivative of g plus 1 over z times the first derivative plus z squared minus alpha squared divided by z squared g of z. So we see the only point that is singular is 0, and sort of the first coefficient has a pole of order 1 at 0, the second coefficient the pole of order 2, so 0, which is the only singular point, is actually regular singular. And of course we can also ask, well, what about infinity? And we can do like a Möbius transformation. So like t is 1 over z, and then we will get that infinity is also a regular singular point. So what we can do now is we can guess g of z is equal to some slightly generalized power series an z to the r plus n, and then the first derivative note that we're now not starting at 1 because the first term doesn't actually drop out. An z to the r plus n minus 1, and the second derivative is r plus n minus 1, an z to the r plus n minus 2. And, well, we can multiply our equation through by z squared. And then we just get this. And if we now plug in our power series, we get that the z squared in front of the second derivative kills our minus 2 here. The z in front of the first derivative kills our minus 1 here. So we end up with n0 to infinity r plus n r plus n minus 1 plus 1. So r plus n minus 1 from here, 1 from here. an z to the r plus n. Oh, and then maybe also just minus alpha squared from the constant term, plus, and now we have our only contribution with like shifted stuff, which is this. And, well, we can split off the first two terms from this sum. So then we have r squared minus alpha squared times a naught plus r plus 1 squared minus alpha squared a1 z plus, and then we have a sum from 0 to infinity r plus n minus 2 squared minus alpha squared an plus 2 z to the r plus n plus 2 plus the sum an z to the r plus n plus 2. In other words, 0 equals to r squared minus alpha squared a naught plus r plus 1 squared minus alpha squared a1 z plus the sum r plus n minus 2 squared minus alpha squared an plus 2 plus an z to the r plus n plus 2. By sort of leveraging linear independence, we get r squared minus alpha squared a naught is 0, r plus 1 squared minus alpha squared a1 is 0, and an plus r plus n minus 2 squared minus alpha squared an plus 2 equals 0. Now, since we can arbitrarily choose our r, we can as well choose it in such a way that our leading coefficient a naught is not 0, so we really get this equation. In other words, r is equal to plus or minus alpha, and when this is the case, then of course r plus 1 squared is equal to r squared plus 2r plus 1, which is alpha squared plus or minus 2 alpha plus 1. If we subtract alpha squared, we just get this, which, except for alpha being minus 1/2, is never 0. So, except for in this one case, we get a1 is equal to 0. And of course, our recurrence relation is then an plus 2 is equal to minus an divided by r minus 2 plus or minus alpha squared minus alpha squared. Not r, n minus 2. So this is n minus 2 squared plus alpha squared plus or minus 2 alpha n minus 2 minus alpha squared So that is minus an divided by n minus 2 times n minus 2 plus or minus 2 alpha. Or if we do a little index shift, we have for n bigger than or equal to 2, an being minus an minus 2 divided by n times n plus or minus 2 alpha. And note that we only have even coefficients because a1 is 0 and therefore a3 is also 0 and so on. So first thing to do is we get rid of this kind of only having to consider even coefficients. So we are just turning this into a power series in terms of z squared. And then we have bn is minus bn minus 1, 2n, and then 2n plus or minus 2 alpha. We can factor out 1/4 and get bn minus 1 divided by n plus or minus alpha. So if we iterate this, you can see that if we sort of plug this in again, we get another factor of minus 1/4 in front, bn minus 2, and then we have a factor of n minus 1, and then n plus or minus alpha, n minus 1 plus or minus alpha. And if we do this a couple of times, we sort of get a factor of minus 1/4 for every time we reduce bn minus s, and then for every time we reduce we get a smaller factor. So we have n minus 1, blah blah blah, until n minus s plus 1, making for s many factors times, and then we have n plus or minus alpha, n plus or minus alpha minus 1, and so on until n plus or minus alpha minus s plus 1. So again, s many factors. And if we pull this all the way to s equals to n, we have minus 1/4 to the n b0 divided by n factorial, and the other factor is plus or minus alpha plus 1 plus or minus alpha plus 2, and so on until plus or minus alpha plus n. And if we want to, we can write this as minus 1/4 n b0 divided by, we can write n factorial as the rising factorial of 1, and this product here as the same thing of plus or minus alpha. And then we get as our solution g of z is equal to n from 0 to infinity minus 1/4 to this n 1 divided by rising factorial of n, rising factorial of plus or minus alpha, and then z to the plus or minus alpha plus 2n. And this is what is generally called the plus or minus alpha Bessel function. And of course there are some problems with this solution, because if you have paid attention, you might notice that if we choose minus alpha, and alpha happens to be a natural number, then this denominator might become 0. So then we actually get something different. But of course, if alpha is like a natural number, you can always start at the at plus alpha, because then you're only going to get like here something that's bigger than 0 and here something that's even bigger than 0. So that's not a problem. But then you're sort of missing your second solution, and then that second solution is not given by j minus alpha, because that doesn't really exist, but by y alpha. So that is the Bessel function of the second kind. But yeah, I'm not really dealing with that now.